Okay, in this video I wanted to try to finish up section 2.2. We're talking about limits, and the last thing to talk about is infinite limits here in this section. So let's take a look at an example. Suppose that we have the function f of x equal 3 over x minus 2. Okay, now from what I know from algebra, I can quick sketch a graph. Of course, 2 is not in the domain, right? So x equal 2 would be a vertical asymptote on this graph. I'm going to have a horizontal asymptote at y equals 0. Whenever the degree of the top is less than the degree of the bottom, you always have a horizontal asymptote at y equals 0. Now, degree just means largest power of x that we see. Okay, so I've got a degree 0 divided by a degree 1. The degree of the top is less than the degree of the bottom, so y equals 0 would be a horizontal asymptote. Okay, I've got the asymptotes drawn. I can plug in values like if x is 0, y would be negative 3/2. If x is 1, y would be, if x is 3, I get 3 in return. Here's 3, 3 on the graph. Okay, I could plug in 4. I create this picture here. Now suppose I want to know the limit as x approaches 2 from the left of f of x. Well, if I'm on the left side of 2 and getting closer to 2, the y values are going to be getting very large but in the negative direction, right? The curve is heading downward, but it's never going to get to this vertical asymptote. Because the y values are growing without a bound in the negative direction, the value of this limit would be negative infinity. How about the limit as x approaches 2 from the right of f of x? Well, if I'm on the right side of 2, the y values are going to be increasing without a bound. Since the curve is heading up the vertical asymptote, you're approaching infinity. The limit as x approaches 2 of f of x does not exist because you're shooting off in different directions there. Remember that a limit has to exist if you're approaching the same y value on either side of x. Okay, here's another one. Find the limit as x approaches 0 of 1 over x squared if it exists. Okay, so here's a graph of 1 over x squared. X can't be 0, right? So I've got a vertical asymptote at x equals 0. There's also a horizontal asymptote at y equals 0. I've got a degree 0 divided by a degree 2, and as I mentioned earlier, whenever the degree of the top is less than the degree of the bottom, y equals 0 is a horizontal asymptote. If x is 1, 1 over 1 is 1, so here's 1, 1 on the graph. If x is negative 1, negative 1 squared is 1, 1 over 1 is 1, here's negative 1, 1 on the graph. Okay, of course the curve has to flow with the boundaries there. And suppose I want to know the limit as x approaches 0 of 1 over x squared. Well, if I'm on either side of 0, the y values are increasing without a bound, right? You're going to get infinity. And now how about this one? What if we had the limit as x approaches 1 of negative 1 over x minus 1, the quantity squared? Well, I can use what I know about transformations. Okay, I'm not going to sketch this graph, but if I were, that would be very easy to do. The negative in front of 1 over x squared would mean that I'd flip this graph about the x-axis, and then the minus 1 here means that I would shift to the right 1 unit with all the points. Okay, so 2 transformations would be applied. Now, these asymptotes are going to move, right? You're going to have a vertical asymptote at x equal 1. So 1 is not in the domain. But because I'm essentially just flipping what I see here upside down and then shifting to the right 1, on either side of x equal 1, the curve is going to be heading downward, getting closer and closer to negative infinity. Okay, there's me growing without a bound in the negative direction, I should say. So the value of that limit would be negative infinity. Okay, here's a definition. A limit in which f of x increases or decreases without a bound as x approaches a is called an infinite limit. Okay, if f of x approaches infinity or negative infinity as x approaches a from the left or a from the right, then the line x equal a is a vertical asymptote of the graph of f. Okay, so there's a connection between infinite limits and vertical asymptotes. We'll be using that, okay? And that can be helpful when it comes to graphing. So let's take a look at an example. Suppose that we want to work with the function g of x, which is x squared plus 1 over x squared minus 1. Now, from what I know from algebra, I can know right away that x equal 1 and x equal negative 1 are vertical asymptotes, right? Because 1 and negative 1 are not in the domain of g. Now, what if I wanted to find the limit as x approaches negative 1 from the left? So knowing that I've got a vertical asymptote at x equal negative 1, and I'm only on one side, I can know right away that the value of this limit is going to be either infinity or negative infinity. I just got to figure out which one. There's a couple of different ways that I could figure this out. One option would be to use a table. Okay, if I'm on the left side of negative 1, but I'm close to negative 1, I can select some values and plug them into g and see what the output looks like. So that's what I've done here. Now in my calculator, if I were to go to y equals, I've already typed in that function that we need here, and I can go to the table there. I guess I've already typed in one number. So what if I were to let x be negative 1.1? Okay, I'm going to get closer to negative 1 on the left. I'm getting 10.525. Okay, and I can plug in some other numbers there. Now notice that the output values are getting very large. They're also positive, so I would conclude that infinity would be the value of that limit. How about the limit as x approaches negative 1 from the right of g of x? Well, again, I know that there's a vertical asymptote at x equal negative 1, so, and I'm only on one side, therefore I know that this limit is going to be either infinity or negative infinity. I just got to figure out which one. So again, I've set up a table here as an option, and I'm on the right side of negative 1, but close to negative 1. And I've selected some values, getting closer to negative 1 on the right, and I can see the output here. Now it looks like from the table I'm producing output values that are growing in the negative direction. So I would conclude that the value of that limit would be negative infinity. The limit as x approaches negative 1 of g of x, that does not exist, right? In this case here, you'd be shooting off in different directions on either side of x equal negative 1. Now, remember what I had said earlier, that a table is only allowing us to guess the value of a limit. Now, in the case of an infinite limit where you've already concluded that, hey, the answer is either going to be infinity or negative infinity, you know, a table is an okay option in my opinion. But a graph is also helpful in determining limits here. So here's the graph of g of x. Okay, I've got the vertical asymptotes there at x equal negative 1 and x equal 1. Now the degree of the top is the same as the degree of the bottom. Whenever that's the case, you're going to have a horizontal asymptote, but it's not going to be at y equals 0. It's going to be at y equals some other number. The easy way to see that is to just compare the coefficients in front of the leading terms. So I've got a 1 in front of x squared up top. I've got a 1 in front of x squared down under. 1 over 1 is 1. Y equal 1 would be the horizontal asymptote. Okay, I've got that written there. And so then I've plotted some points. Of course, that information from the table that I've already got going on here allows me to plot several points. And another observation here, g of x is going to be symmetric to the y-axis. Since g of negative x is the same as g of x, right? So negative x squared is the same as x squared. Then you're going to have a graph that would be symmetric to the y-axis. Okay, and that can be nice to see here because ideally it would reduce the amount of point plotting that we would need in this problem. And you can see that if I'm on the left side of negative 1, the output values are going to be getting very large in the positive direction. Okay, if I'm on the right side of negative 1, the output values are going to be getting very large in the negative direction. Okay, you're shooting off in different directions there on either side of negative 1, so the value of that limit does not exist. Okay, here's another one, y equal x plus 4 over x plus 2. So again, from what I know from algebra, I can know that x equal negative 2 would be a vertical asymptote on this graph. Now, you can sketch a graph, okay, or you can use your calculator to sketch a graph. Another thing that I would add too is, in the case of using a table, like you can build a table, but in some cases, it's going to be just think about the problem and see what the behavior of the output values look like. Okay, so like here, suppose I wanted to know the value of the limit as x approaches negative 2 from the right of x plus 4 over x plus 2. Well, knowing that x equal negative 2 is a vertical asymptote means that I can know right away that the answer is either going to be infinity or negative infinity. I just got to figure out which one. Now, x close to negative 2 on the right means that the numerator is going to be positive, right? If I'm on the right side of negative 2 and I add 4, no matter what number I select, I'm going to have a positive number up top. That will always happen. And the denominator will be a small positive number. Okay, if I'm on the right side of negative 2, like x is, negative 1.5 or negative 1.9 or something like that, and you add 2, you're always going to have a positive number down under. Now, that number down under is going to be a very small number as long as you are close to negative 2. The closer that you are to negative 2, the smaller that denominator will be. A positive divided by a small positive would produce a very large positive value. Okay, so the values of y become very large positive numbers. Therefore, infinity is going to be my answer there. Okay, so I don't need to write a table. I don't need to sketch a graph. I can just think about what's going on in the behavior of the output values there. Let's take a look at another example. Okay, f of x is x squared plus 2x minus 8 over x squared minus 4. I have written down some limit calculations that I'd want us to compute here. Now, be careful with identifying the vertical asymptotes, okay? 2 and negative 2 are not in the domain of f. However, this function is not in complete simplified form, okay? X equal negative 2 is going to be a vertical asymptote. X equal 2 is no longer a problem when you simplify. Right? So you're going to have a hole in the graph at x equal 2. These factors of x minus 2 are going to cancel, allowing me to conclude that I'm going to have a hole in the graph at x equal 2. Now, before we look at these limit calculations, just real quick here, y equals x plus 4 over x plus 2, and f of x equal x squared plus 2x minus 8 over x squared minus 4. These are not the same thing. Now, one's simplified to be the other, but they are not the same thing because they have different domains. Okay? As I mentioned right here, 2 is no longer a problem. Well, that's not the case originally, right? 2 is a problem over here. Okay? So 2 is the one number that actually makes these different. If you don't use 2, then they are exactly the same. Okay? But just take note that these are not the same thing. Okay? 2 is the one number that makes them different, right? Now, they're very similar, of course, okay? In fact, if you throw away 2, it's like you're graphing y equal x plus 4 over x plus 2. X equal negative 2 would be a vertical asymptote, and I've got that. Y equal 1 would be a horizontal asymptote, okay? I've also plotted some points to draw this graph. Now, if x is 2, 2 plus 4 is 6, divided by 4 is 3 halves. Okay, 2 3/2, that point is not on the graph. So you're going to have an open circle there. Okay, and here'd be just a quick sketch then of the graph of f of x. Now, what if we wanted to know the limit as x approaches negative 2 from the right of f of x? Well, that's going to be infinity, right? If I'm on the right side of negative 2, the curve is heading up the vertical asymptote there. How about the limit as x approaches negative 2 from the right of f of x? Well, that would be negative infinity, right? These two calculations here are essentially working with this model here, x plus 4 over x plus 2, right? As long as you're not using 2, then these functions are the same, right? Now the limit as x approaches negative 2 of f of x, that does not exist since you're shooting off in different directions there. 2 is the one number that makes these different. Okay, so the limit as x approaches 2 of f of x, well, that does exist. Even though I've got an open circle there, I don't care what's happening at 2, I care what's happening around 2, right? That's the whole idea of a limit. We want to know what's happening around this number as we get closer to the number on either side. Well, it looks like if I'm on either side of 2, the y values are getting closer and closer to 3/2. So the value of that limit would be 3/2 then. Here's my last example in the section. Suppose that we have the cotangent function. Okay, cotangent x is the same as cosine x over sine x, and I can use that in this limit calculation here. Suppose I want to know the limit as x approaches pi from the left of cotangent x. A couple of options that I can use to figure that out. Now, cotangent x is the same as cosine x over sine x. Here's a quick sketch of the graph of the cosine curve, and here's a quick sketch of the graph of the sine curve. Now, because sine x is in the denominator, I would know early on here that there's going to be some vertical asymptotes on the graph of the cotangent curve. And anytime I've got vertical asymptotes, I'm going to have infinite limits then, okay, and vice versa, right? Anytime I've got an infinite limit here, I'm going to have a corresponding vertical asymptote. So let's see, sine x equals 0. I know I can't divide by 0. Sine x equals 0 means that x is 0, x is pi, x is 2 pi, x is 3 pi, x is negative pi, right? There's going to be infinitely many vertical asymptotes created on the graph of the cotangent curve, since there's going to be infinitely many times where sine x would be 0. Okay, x equal n pi would be the intercepts on this graph. N is an integer. And so on the graph of the cotangent curve, you're going to have vertical asymptotes at x equals 0, x equal pi, x equal 2 pi, x equal 3 pi, etc. Now, pi is this a value here, and I'm interested in what's happening on the left side of pi. Knowing that there's a vertical asymptote at x equal pi means that I can know right away that I'm going to have an infinite limit here that I'm working with. So the answer is going to be infinity or negative infinity. Well, I've got a graph of the cotangent curve drawn. I don't really need that, although that is an option. Okay, I could use just the graphs of the sine curve and cosine curves here. So if I'm on the left side of pi, cotangent of x would be a negative, right? If you're on the left side of pi, you're down here. As long as you're close to pi on the left side, you're going to get a negative value. If you're on the so the numerator is going to be a negative. Okay. On the graph of the sine curve, if you're on the left side of pi but close to pi, you're going to have a positive y value. Okay, so we have a negative divided by a small positive. It's going to be a small number because the y value would be close to 0 here. Again, if you're close to negative to pi on the left. A positive divided by a small negative, excuse me, I'm saying that wrong. A negative divided by a small positive would produce a very large negative. So negative infinity would be my answer. Okay, and I've kind of summarized that right here. Now, of course, another option would be to use the graph of the cotangent curve. So I've drawn that. Okay, if I'm on the left side of pi, the y values are getting very large in the negative direction, right? This curve is heading downward, getting closer to the vertical asymptote. So negative infinity would be my answer. The point is to say that, when you're working with limits, there is options, okay? Be careful about a table, though. I'll have more to say about that in the coming sections. A table is something that we want to pull away from. It's a very poor option, okay, in general, because you're guessing your answer. But in the case of infinite limits, it's an okay option if you've already concluded that, hey, the answer is infinity or negative infinity, okay? Graphing or making an argument just by observing the values of the output is some other options, though, that you can consider. Okay, so the homework in this section is on page 92. Be sure to look at the odd numbered problems that are listed there on page 92 for me.